So I'm just going to go over what I've been doing with H5 Bench, and I'll kind of describe what H5 Bench is all about. So some of you may know that we have an HDF5 IO test, and basically that allows you to cycle through a whole bunch of different IO IO patterns. And the difference between this H5O test and what I'm going to talk about, which H5 Bench, is basically H5O test is kind of made up. It's not based on application. I mean, it's kind of loosely based on application, but it lets you really, it's just to cycle through kind of made up configurations to see the performance. Whereas now, if you're curious, HDF5 IO test is on GitHub, so you can download it and test it for yourself. And there's been past talks that go over how to use it. Instead, I'm going to talk about H5 Bench. So this is a project between LBNL, and I think some of it's funded by ECP and some external funding. This is basically loosely based on actual applications. So it first started off with VPIC, which is a particle simulator, and it kind of grew into adding more and more different application IO patterns from actual applications. And so that is also on GitHub. And basically, as it says, it's just a parallel IO benchmark for HDF5. So it's similar. So if you go, then they have a read the docs, and you can kind of know what the current different IO patterns are. Let me see, where are they? They have VPIC, which is what they call the H5 bench or H5 write, H5 read. One is, so VPIC would be the writing. And then there's another program that does the reading that is based on. It also has the IO pattern used by Amerex and Open PMD Exerciser, and then E3SM, which is another big user of HDF5 for really large simulations. So you can build, if you build H5 bench, you can choose to also build these other IO patterns. But for this talk, I'm just going to focus on VPIC or H5 write and read. So in order to do that, it has a overall JSON file that you can control how to use it, or you can go in and there's a file that an input file that you would create, and it has let me scroll up here. It has the different patterns you can choose to test. So you can test contiguous data sets. You can also test interleaving. So you could get better performance if instead of writing separate data sets, you combine them all into a struct and just write out that one struct. That's what they call interleaved kind of pattern. And you can have a different memory pattern than you have in the file, or vice versa. So if you want to have contiguous in the memory and file, you could see what performance hit you would get if you did that. There's also, you can check out different dimensions. So you can do 1D arrays, and you can go up to 3D array patterns. And then you could also test out whether you want to do independent or collective. And we added subfiling, so you can choose, and that's what I'm going to talk about, subfiling results with H5 bench for subfiling. But you can choose to do subfiling. There's also have async APIs that you can test, and you can put a pseudo computational time in. So you say wait 2 or 3 seconds while to simulate the computation while the async is going. So that's what this means by emulated compute time. So for this case, they have 4 seconds between the actual IO, so it can do some async calls. So you can test out also async APIs with this program. So I'll just give you an example of what an input file looks like. So again, you select what operation you want to do, whether you're doing reading or writing. You select what memory and file pattern you're using. So for this case that I'm going to show, they're both contiguous. The number of particles, that basically affects the size. Actually, that's been obsolete now. The number of time steps, you could do multiple time steps, so you can get the statistics over more than just one time stack, which is usually good because most of parallel file systems have some kind of variability between output dumps or reading, writing. Then you can decide if you want to do collective IO and whether you want to do collective metadata operations. So usually this is always the case, but if you want to turn it off and see what happens, you can try that. Then this is where I can mention that you could do a data set that's just one dimension, and this would be the size. So this basically scales up as the number of ranks, for at least for this case. So if you want to do 3-dimension arrays, then you can do the same amount of data by just adjusting your 1, 2, and 3 dimensions. This is the file, so it writes out CSV files, so you can visualize it in Microsoft or whatever program that reads that. I usually use GNU-plot, so I process that. And then in order to turn on subfiling, and just put the keyword yes. And that's basically all you need to do to run H5 bench. So let's go to the results. So I ran this on Summit H5 bench, both read and write. So we'll first look at just playing with, so let's look at the write first. So I checked doing independent and collective and doing 1D arrays or 3D arrays. And then I did the same with subfiling, and there's no collective with subfiling, it's just independent, so you don't have to check that. So this is the observed write rates. They went from 1,000 to roughly 5,000 ranks. And you can see that the bars just indicate, so I did 5 runs of each case. And this is, so this is the observed write rate. And the bars just indicate the min and the max for each of the, over those 5 runs, and the bars are actually the average between them all. So you can see the advantage of subfiling as you start to increase the number of subfiles. Or this is default subfiling, so it just uses 1 subfile per node and all the other defaults. But it is aligned though, along the file is aligned along the stripe size. Well, actually this is GPFS, so you don't have to set that. But it does use stripes in the subfile itself of 16 megabytes. So it's pretty good this for the write. The read, let's see, observed reading here. This I'm gonna have to have someone look into this. So this is the observed read rate. Again, we did the independent collective and then the subfiling. And for this, we're not getting as good performance for the reading as we did with just doing a subfile, 1 shared file for all the ranks. It's pretty good. It's getting over gigabytes per second. So it's not terrible performance, but the subfiling we need to work on why this is not behaving as it should. But there's really no difference between either doing 1D or 3D for the most part. It's kind of within the noise. So at least for this case, it doesn't really matter if you do it between 1 and 3D. Now, if we just look at some subfiling parameters, let's see this. So this is doing, this is now just doing subfiling itself. And then I did 1D and then 3D. And then I changed from going from 1 subfile per node to 4 subfiles per node. So the red and then the green is with 4 subfiles. And this is the observed write rate of the same number of ranks on Summit. As you can see, the performance boost you get if you have more subfiles per node. And here you can see a difference between doing 1 is the red, and 2. So there's a little bump for using more, at least on Summit, if you use more than 1 subfile per node. And this ranged from 120 gigabytes, I believe, total for 134, and then 3 terabytes for 5,000. So they're pretty large. So it's pretty large amount of writing per node. And then if we look at the read rate, again, you see a bump between using 4, although here it's still at the 5,000. They're kind of the same for 3. So there's a little difference between the 3D and the 1D, but they're basically the same. But again, you see the trend of having more subfiles. It seems to be a little better. Yeah, so this is currently what I've got for subfiling with H5 batch. We're running on Polaris, but those runs haven't run. We're still waiting for results. Any questions about that?
Can you go back to the right, the one before this? Because if I remember correctly, what's interesting is that the volatility or the variability is so much greater.
Yeah, I think it's just Summit. Summit seems to be very GPS. Maybe it's just a GPS thing or GPFS. But let me see if I can find that.
I mean, it looked like here it's maybe 10-15%, but for the writes here, I mean, it's
it goes from 300 to
like 30% or and
yeah, it's always been that way. That's why I had to do a lot more. I mean, you get in trouble if you just do one time through, because it can be very deceiving what the performance is. So you really have to do more than once. But we do the same thing in IO test, right? And I think IO test had the same variability, so it didn't have anything to do with this. It was still, I think, let me go back to. Yeah, even without subfiners, but it's definitely not as large variability. This, I think it gets even worse as you add more ranks. The variability is pretty. This is huge. I mean, it goes from 50 to 350. Yeah. Yeah, with sub, I guess we'll have to check why this is doing as well with subfiling, because you don't see that kind of variability with the others. We're not using subfiling.
Yeah, that's yeah. There seems to be, and yeah, it's the number of ranks plus subfiling. It's both. Yeah, you would. Yeah, the number of ranks certainly amplifies this, but then it's also something to do with subfiling.
Yeah, it could be I mean, it could be, since one node, I don't know why. Well, you would think it'd be better. It wouldn't be as variable because there's only one. I mean, there's only one thread doing the actual IO, right? So it's whereas here there's all the ranks are doing the IO, and here there's less number of ranks, so you think it'd be less variability. Maybe there's some kind of locking that's happening at the file system. We are testing using no local storage, because you can run no local storage on Summit and Polaris. But I haven't got those results yet.
Interesting.
For some reason on Summit, I was trying to copy the files back to make it an HDF5 file and see whether, because with Subfiling you have to combine them back, the files, to make a valid HDF5 file. So I kind of wanted to see how much time that took if you were doing it on a local storage and then writing your actual HDF5 file on the parallel file system. I kind of want to see how long that would take. But you have to submit that as a job, because each node, I mean, you have to do it as an afterthought, because each node, unless you put it in your program itself to make a system call, you'd have to run a job too, because each node doesn't have access to any other node's memory or local storage. So, but yeah, there's a few things we have to iron out, I think, with subfiling, and hopefully we'll do that in the next year. It's part of the ECP project, is really start to perform tune subfiling. But I mean, in general, it behaves much better.
Yeah.
That's all I have.
And then can you go back maybe to that read figure where subfiling just didn't seem to have any effect, or
yeah, it's pretty bad.
here or be counterproductive, rather than
It would hurt you to use for reading. It'd hurt to read. So I mean, you'd probably want to put the files back together and do reading as you normally would. You'd get better benefit from doing that. But if you want to do a checkpoint start, that would hurt you. So we have to find why it's doing that.
And could it be something to do with caching or prefetching, or
it could be, but the problem is, I mean, when I run H5 bench, I run it once per through and just rerun it. So I'm not running the same program. So I guess I was hoping it would flush the cache if you run it a new executable each time, instead of you using one executable and looping over the same. Then you might be able to cache stuff, right? So there's no way to clear out a cache, I don't think, at least if I remember it on Summit on GPFS, just to disable it. So I don't know, and it's pretty big. These are pretty big files, so I don't think it's cache. But we just don't know.
Yeah.
I think Jordan has some ideas how to improve reading, because I think we saw the same kind of behavior on Polaris. So I'm not sure it's a Lustre GPFS issue. Yeah, but it's one of the things we're going to look into. And hopefully when Frontier comes on, then we'll get, well, it's the same file system. So we'll see if it's a different architecture, but they're using the same file system as Summit. So we'll see if it has the same behavior.
Yeah, puzzling.
Subfiling is kind of big that way.
But in this one, it's also interesting, the variability with subfiling is actually tiny compared to the other variabilities. So that's remarkable. And
it probably means that there's some barrier in there that's causing it to sync. That's probably why the performance is so bad. They're all waiting for something to happen, which it shouldn't be the case for reading. I wouldn't think there'd be much blocking and reading.
Yeah. But it looks like, it's just maybe less than 10%, whereas for everybody else, it's really through the roof.
Yeah, this is like, you can get really good performance and not really good performance. And yeah. Is there any other general questions about HDF5 or?
And sort of just for that last graph, what's that, the second, the bluish, the navy, what was that again? It was 3D or 1D collective.
Yeah, so the darker is 1D, the lighter is 3D.
Yeah, that's sort of strange that there's such a drop for the 5,300 rank.
Yeah, for collective, I don't remember. I thought independent for Summit gets better as the number. I think collective gets worse as you increase the number of ranks on Summit. So I think independent, I think this is kind of the transition between 10,000 ranks. I think independent, at least for this case, starts to be better than collective. But at some point it has to get worse, I think.
Yeah, yeah.
But
Yeah.
I think we went up to 50,000. It was still pretty good, especially with subfiling. I mean, subfiling at 50,000 does very well. So at some point,
Mhm.
I think it independent would start to not perform very well, but it does perform much better than collective for some reason, at least on Summit.
Yeah, yeah. And the strange thing though is that 3D, again, dimension shouldn't really matter, but for 3D, the picture is almost the opposite. But then again, looking at the variabilities, they are just so large that, yeah.
Yeah, it's hard to make a decisive
Mhm.
conclusion.
Yeah, yeah. Hmm.
It is kind of good news because when I implemented Cabana's IO, I used 3D arrays. I was kind of glad to see that using 3D arrays doesn't hurt you. So that's
Mhm.
good. I mean, for Cabana, you can do scalar, and they have 1D and they have tensors. And the tensors, I didn't bother splitting them into components. I just wrote the whole 3D array. So hopefully that performs well. Yeah, Cabana is very similar to what VPIC is. It's a very similar code, so it's very similar output. The reason why we have compound in VPIC is because it performed much better than writing each. I think there were 9 data sets instead of writing those individually. Compound. The problem with that is we used XDMF to read it, and XDMF doesn't understand what compound.
Mhm.
So that's why I didn't go that route with Cabana.
Cool.
Any other? Guess I'll stop sharing.
Okay.
All
Well, I
right.
guess
Dana, you'll be the next call the doctor. Do you have a preview of what you're going to talk about? I feel like we might have news by then, right?
Well, we'll have the 114 release will be out. So I don't have anything specific besides that.
Yeah, that'll be something.
Yeah.
Okay.
are you gonna go over the 114 features and stuff like that, or
Yeah, I think we'll go through like them because we can go through the change log. We'll
okay?
just talk about like what's in it and stuff like that. And
All right. Sounds good. Thank you, Scott.
Yep.
Mhm.
Thanks everyone for joining us.
see you in the new year.
All right.
Thanks.
Yep.
Bye.
Bye.
See you in the new year. Bye.
Wow.